I'm Mark Sever. I'm coming from Danfoss. I'm part of this global application experts, and my main focus are food retail systems. Today I will present you two tests what we performed on one real system which is built in Denmark, where it's part of our application development center. So where we are looking for the new technologies and new ways how we can transfer energy in such application. So as I said, on the most left corner, you can see it's a real supermarket just next to our main building. And here are technologies what we implemented. And today I will focus a lot on this, we call it advanced energy pack, where we are producing refrigeration technology, air conditioning, heating, but also, of course, we have photovoltaics. Well, we can separate the system in kind of three layers. First layer is a cooling grid, where we are producing refrigeration and also cold water for the air conditioning. We have also cold storage vessel. There is also heating grid, because the store, but as well also the some small office areas what we have there, and also presentation rooms, also we need a heating. What is important for this story is it is connected to the external heating grid. It means district heating, which gave us some opportunities. And when we talk about electrical grid, I mean, it's standard, you need electricity on such system, but also we have a photovoltaic on the roof of that store. Just to simplify things, here is the very simple scheme of this advanced CO2 energy pack. We have compressors and we put, let's say, on each compressor a variable speed drive, because actually it's a pretty small system looking from the load perspective. But we put all these technologies so to be able how this system could perform on a medium to big size supermarkets. We have a heat recovery part, which is, let's say in total we can produce around 50 kilowatts, which is necessary for the store, but also for this building, which is next to this store. We also have a possibility to produce cold water for the air conditioning. And also we have some add-on things to do ice melting during winter time, and also we have possibility to have a ground heat sink, which can use for the ground subcooling, but also we can use it as a heat sink when we need to produce more heat during winter time. We also have ejectors here implemented, where we are using different ejector technologies like high pressure and liquid ejectors. All in all, it's a very small, very complex system with intention to show and to test different technologies for the bigger systems. This is the, let's say, photo of this system, but what is essential for this first test is that we actually created digital twin. So we made a model of that system, of course adding all these compressors, polynomials, and also all the valve technologies what we have, also injectors and everything. And we made a model how this system can perform in different ambient conditions and what we can gain from that system. Based on this, this test, what I would like to present you, is focusing on a heat recovery and how we can utilize this system to produce heat for the necessity what we have on the store, but also with the option to sell this heat, to resell heat to the district heating system. Very similar like you have with today with the photovoltaics. You are using energy for yourself. If you have a surplus, you can sell further. So we have a heat recovery unit, which is having controller, which is providing heat for the consumers. This request for heating is coming to, let's say, one PLC, what we put in the between, which is actually transferring this signal, and then here we can manipulate this signal in a better way. And then it goes to the controller dealing with the refrigeration system, which has an action how we will run our heat recovery process in a CO2 system. We will produce heat, which will be then delivered to the heat consumers. We have an option to take additional heat from the district heating, but in this test we didn't have pull out this heat from the district heating, but we were testing this possibility to resell heat to the district heating, because we have possibility to produce even more heat than what we need for our consumers. In the model, we also took of course, in equations, how much we can produce electricity from our photovoltaics, but also what is the price of electricity. And in Denmark, price for electricity is changing every hour. Looking also on the weather forecast, because it has, of course, quite big influence on how much electricity you will produce, and what will be ambient temperature in this area, and also what is the heat energy price coming from the district heating. So all these kind of inputs are valid for this analysis and tests. What is the point? When we are running system, when we are just providing heat for the local consumers, our water return temperature is on the level of 25 degrees, which gives us possibility to completely recover heat from the CO2 system, which can be delivered to our consumers. But from other side, if we are trying to sell this heat to the district heating, the water return temperature is on a much higher level, and typically it's on around 43 degrees Celsius. It means we cannot deliver all heat to the district heating, but just partially, unless we go to the very high pressures in the system, which was not our intention. So we were looking how to balance between these two, let's say, levels. I mean, providing heat to the district heating, but also then adding this heat which will be used for the local consumers. So if you can notice here, so majority still we are able to deliver to the district heating, but the rest we will produce for the local purposes. But if there is no heating demand for the local purposes, because, for example, it's summertime, then we need to deliver this heat to the ambient, otherwise system cannot run. So we have this kind of, let's say, activities between those two, let's say, extreme conditions, and we put all this in our, let's say, digital twin model to be able to manage this further analysis. But the store was open, let's say, in July 2023. So all this analysis was done based on historical values about the ambient temperature, and what is also very important, the price ratio between the electricity price and the district heating price. So this black line here, I don't know, do you see this line here? This is actually this price which goes for the last 3 years. And as you can see here in the 2021, the price ratio was fantastic, which gave us, let's say, virtual opportunity to export a lot of heat. This green color, it's a heat what we could export because the price of electricity was quite favorable. And yeah, we could have a very good possibility to earn a lot of money by selling heat. But then in 2022, as we know, there was quite a big dynamic on the European market with those prices. And actually it shows that during that year, very limited amount of heat we were kind of able to sell in such kind of environment. In 2023, these price levels were kind of stabilized, which gave us possibility virtually to sell this heat. So this was analysis what we did based on this modeling. But what's the point is, of course, we did a test now on the real system to confirm is our model correct or not. And this is one example what we did in a 2 weeks operation, where you can see here the red column is operation without heat export, and then the gray is with the heat export, because we are able now to model each of those consumption. You can observe the daily average ambient temperature, how it goes, but also how the price of electricity or price ratio, electricity and district heating, how it goes up and down. And it shows us these differences in this operation costs, I mean in some money, in euros in this case, how much we can save by selling this heat to the district heating and making our running costs lower. As you can see here, it was not all the time favorable to do this because the prices were going up. So in this, let's say, area, it has no sense to sell this heat back to the district heating, but only when we had this good ratio between the prices, which also have an influence also by this ambient temperature, because by ambient temperature you all have different conditions in the CO2 system. So it was quite dynamic operation, and we had this, as I said, once, let's say, programmable PLC, where we add all these features, and then the system was optimizing in that way. As a conclusion of those tests, we saw there is possibility to decrease operation cost by 10 to 50% by doing this kind of heat mode operation, where we can resell this heat in this way. Of course, in Denmark there are a lot of these district heating systems, so there is a kind of very good idea to do it. In rest of the Europe, maybe this is not the case, but it could be also opportunity maybe to resell to the rest of the building, for example. The next test, what we did, we used actually quite old feature which is available in our controller, is this rail heat dew point control, where you are measuring relative humidity in the store, and based on this you are controlling your rail heaters on the low temperature cabinets typically, and you can manage those rail heaters according to humidity and dew point temperature at the end of the day. We noticed that this feature is rarely used. It's present in the controller and you have possibility to do it, but very typically contractors are not utilizing them. With those tests, we would like to present you how much you can save energy directly on these electrical heaters, but what is even more important is how it influences on the compressor consumption, which was something very often neglected. So what do we do here? So this is this store. We have these 4 minus islands where we set this control of those rail heaters. On one group we put, let's say, possibility to do maximum savings, and on a second group we do this kind of more robust control, so to be very sure not to have a condensation of these glasses there. And simply we measured consumption. If you go to the most left, so this line shows the total consumption when these rail heaters are always on, and very often we see on the systems that these rail heaters are on all year round. So every day in the year, 24 hours, it's always on. But when you don't have such high humidity in the store, it's not necessary. So you can manage this operation in a much better way. The consumption of those rail heaters is, the power is 2.6 kilowatts. And then if you multiply this, 24 hours, 365 days in the year, you get yearly consumption. As I said, it's relatively small system, but again, it's a lot of energy. These peaks, what you have here, these are defrost cycles. So during defrost, the rail heaters are engaged, of course, but then we have this level when we can save a lot of energy. It's very simple calculation, but the point is, let's look how it influences on the compressor operation. So if you look the left chart, you can see operation with, let's say, 30% engagement of these rail heaters. So these are days with less consumption. Then we have a higher consumption when rail heaters are 100% loaded, and then again when it's low load. So on the compressors, because we implemented this P-optimization feature, which is adapting a reference for the compressors according to the most loaded cabinet, you can observe that during this, let's say, full load, rail heat full load, the reference for the compressors dropped. Of course, this means the consumption on the compressors increased. Coming to the point, when you look how it influenced the load on the low temperature cabinets, you can see that the cooling demand on the compressors increased by 28% when you have rail heaters on. I'm talking about load on the low temperature compressors. And here, this is analysis looking how much it means, not only on the compressors itself, but also as a sum of load on the electricity on evaporators, including the rail heat, but also the low temperature compressors, but also part of the medium temperature compressors, because in this system, medium temperature compressors has to run to be able to run such a system. So it means, all in all, these rail heaters, when they are turned on, are increasing all this low temperature part by 53%. So it's quite substantial load you are adding if you are just running your system full load without concerning possible savings. Going all around, if you add to this consumption and add medium temperature load, you can observe, looking at these red columns on the compressor pack, looking as a whole load, low temperature and medium temperature compressors and all evaporators as a total, we can save, let's say, up to 30% of the load. Of course, this is something not constant through the year, because in the winter time you have a low relative humidity in the store. It's not the same like in the summertime. But this is, let's say, message. Please use this feature, which is in the controller. It's for free. Only you have to persuade contractors to utilize this and to be realized that the load on the evaporator has a direct also reflect on the compressor operation. And of course, you can do substantial savings if you use these smart functions. As a conclusion, these are controllers which are implemented on such a system, and in our case we have this controller in between, which is managing this operation and let's say synchronization of this heat request signal coming to the PEC controller, and with all these advanced features what we are implemented there. Of course, we have plenty of energy meters on all possible assets to learn where we are losing energy and how we can save those energy. Of course, all this system can be connected to the upper cloud system for further analysis. This is how it looks, this advanced system. As I said, for such a relatively small system, it's over technology, but as I said, here we would like to show all possibilities what you can utilize on medium to hypermarket systems. As a conclusion, if you have some questions, please visit us on our booth in Hall 7 for further questions. We also did some papers, a white paper, talking about this rail heat tests and possibilities, how you can save a lot of energy. Thank you, and if you have any questions, come to me.